In this second question on projectile motion, it goes into it in more depth. This is a harder question. I call it a classic though because it's got almost all of the stuff that you'll find in these. We have a cannon this time. Firing shells or firing cannonballs at distant ships, and cannon is fired horizontally from a height 67 meters above the surface of the water. The ship that's being hit by the cannon is 150 meters away. So you've been given two distances there. Those amounts are repeated up in the question. Right, the first thing they ask you is show that the time taken for the cannonball to reach the water surface is about 3.7 seconds. So all you've got to do is work out how long it takes the cannonball to fall 67 meters, because as we've said, the horizontal motion and the vertical motion are not related. So all we have to do here is quickly pick up our good old equation of motion, and we can have S equals ut plus half at squared, but u, our starting velocity when we're falling, is 0, so u doesn't actually come into this, so it's just going to be S equals at squared over 2. Move that around a bit, you get t squared is equal to 2s, the distance, divided by a, which we'll take as being acceleration due to gravity. So we can pretty much assume here that g we can have as 9.81 meters per second. Pop that into this, and we end up with the calculation. T will be square root of 2 multiplied by that height, 67 meters, and divide by acceleration, 9.81 meters a second. And that will give you an answer of time being 3.696 seconds. And again, you're showing that it's close to 6.7, so that would round to 6.7 seconds. So showing your decimals shows that you actually worked it out. Right, now next bit, calculate the velocity at which the cannonball was fired. Now in this case, you're going from, in this case, this was u vertical was 0, but we don't know what u horizontal is. But we do know that distance horizontal was 150 meters, and this is an unchanging speed. So what we do know is that it took that time of 3.696 seconds, so we could say we've got a time of 3. Okay, I'll do the 696 again. 3.696 seconds. We've got a distance from here of 150 meters, and so velocity horizontal will be distance horizontal, which is 150 meters, and divide that by the time, and I'll stick with my 3.696. Okay, and we get from that gets the answer of 40.58 meters, but we're looking at significant figures here of, well, they're talking about 3.7 there, that's 2 sig figs. In the original diagram it was 150, which looks like 2 sig figs as well. So we better round that to 2 significant figures, which would make the answer 41 meters per second. Now, for our vertical part of the velocity, go back to the old diagram. We've got a u of 0. We have a distance of 67 meters, and we already know what the time was. So we have got we've got u equals 0, we have got s equals 67 meters, and we have time is 3.696 seconds. Right, going back to that, we can then use a different one of our Suvat equations. We can use v equals u plus a t, and because u is 0, that simplifies to v equals a multiplied by t. A is equal to g, which is going to be 9.81 meters per second. So fairly straightforward calculation. We should just have 9.81 meters per second multiplied by that time of 3.696. That comes to 36.26. Right. And we're going to round to 2 sig figs again, and we'll call it 36 meters per second. Oh, sorry, 36 meters per second, yes. And you might just want to maybe point out that that is, of course, downwards, just to be sure that you know what's going on. Next, we're asked to work out the magnitude and the direction of the velocity, in other words, the resultant velocity of the cannonball just before it hit the ship. So going back to this diagram, it's going to be the magnitude and direction of that velocity there. Now, we've already worked out as we went along that if we go back to my original numbers, we've got about 40.586 meters per second horizontal, whilst we have a vertical velocity coming down of 36.257 meters per second. They do like you to go back and reuse your your most precise measurements from before. So we get from that that we have a horizontal velocity of 40.586, and we have a vertical velocity of 36.257. Right. We can then combine those together, and if we did do it as a diagram, that would be our resultant velocity. It would be the hypotenuse of that scale. Now, if you did this as a scale diagram, you could maybe do that as 4.1 centimeters, or do it as 41 millimeters. Do that as 36 millimeters. Measure across here, and whatever it comes out in millimeters, right? That should give you your velocity component, is that measured number of millimeters. If instead you want to do it by calculation, then you use Pythagoras, okay, and you're going to have that that v squared is going to be the 40.586 squared plus the 36.257 squared, and obviously work those out, add them together, and you get that it's the square root of, if you like here, v horizontal squared plus v vertical squared. Right, working those out gets you 54.42. Okay, and take that to 2 sig figs that we've worked on all through, and we'll end up with a reading of 54 meters per second. I did try it, putting in 41 and 36, and you annoyingly get 55. They do quote a range in the mark scheme, so you might still get that. A little bit unclear. For the direction of the velocity, we are going to need an angle to something. So why don't we just say angle to the horizontal, which in this diagram, there's the horizontal, is going to be that there, and you can just bring out your old trigonometry skills and go, right, tan of angle alpha is going to be opposite over adjacent, so it's going to be 36.257, here we go again, divided by 40.586. Work out the tangent and then do tan to the -1 on your calculator, and you end up with an angle of, right, looking like 0.8933. If you do tan to the -1 of that, you get angle alpha itself. Shift tan to the -1, answer equals, you get 41.76 degrees. Right, so again, take it to 2 sig figs, call it 42 degrees to the horizontal. Right, and for this last little bit, they're asking us to calculate a loss in gravitational potential energy. Easiest marks in the question. You already know that gravity potential energy is mass times gravity multiplied by height. They've just given you mass, 22. Gravity we'll call 9.81. Whiz back to the original diagram, it's 67 meters up, so we're going to have 67 meters in there. Right, multiply those together, and you will get 14,459 joules. But beware of rounding that, because they'll be expecting you to do it to 2 sig figs. That rounds to 14000 joules. Okay, so there you go, 1 mark. Now, last part is describe energy changes taking place from when the cannonball leaves the gun up here to when it reaches the ship down here. Now, we've got to be slightly wary, and remember you're doing an A-level question. Just before it hits, it doesn't hit the ship, it hits the water. Just before, so we haven't got to worry about hitting the water, but we've got to do its energy changes from the moment it leaves the cannon. So, when it leaves the cannon, it has got some GPE. These are the changes. We know it's got horizontal EK, but don't worry about that. It's got GPE, right, becoming kinetic energy, or you can say it's got GPE going to kinetic, and then as it's falling through the air, of course, some of that kinetic energy will be converted into sound, quite likely, and of course thermal, or indeed heat. So 2 marks. They're expecting 2 energy changes, or energy transfers as it's fashionable to call it now, including the effects of air resistance. So you can think of the cannonball whizzing through the air going whee, and generating heat. The cannonball will get hotter as it flows through the air as well. And there are your 2 energy changes. Right. Of course, we would also be expected to maybe call it internal energy. So you could say internal energy. All right. Better word for thermal. All right. They don't mention sound specifically, so don't see why not, because it does. But thermal or internal energy, or at worst heat, and that does you.